Made from tubular steel, the towers usually come in 3 sections and are assembled on site. Because wind speed increases with height, taller towers enable turbines to capture more energy and generate more electricity. Winds at elevations of 30 meters, roughly 100 feet, or higher are also less turbulent. Wind, as we all know, is air in motion. And when there is movement, there is kinetic energy. Kinetic energy depends on mass and speed, in the form 0.5 meters v squared. Air speed is easy to assess, but we need to determine the mass of air passing through the turbine. To do this, we will calculate its volume and multiply it by the density. Considering that the blades of the windmill rotate and form a circle, the mass of air that crosses the wind turbine will have the shape of a cylinder. What is the kinetic energy contained in said cylinder? To calculate it, suppose an arbitrary period of time t, during which we assume that the velocity versus remains constant. The base of our imaginary cylinder will be the area of the mill, which as we know is pi r squared, where r is the length of the blades, the radius of the circumference which is equal to the length of the blades plus the radius of the rotor. For its part, the height of the cylinder will be the distance traveled by the air in time t, which will obviously be bt. And since the volume of the cylinder is base times height, we have V equals pi r squared Vt. Do not confuse V for volume with versus for velocity. On the other hand, the mass of air that crosses the wind turbine is equal to the volume times density of the air. We will call the density ρ. Its value is approximately 1.29 kilograms per cubic meter, but it depends on many factors, for example the altitude above the sea. We are already obtaining results. The kinetic energy of the air that sweeps the wind turbine is 0.5 meters v squared equals 0.5 v rho v squared equals 0.5 pi r squared bt rho v squared equals 0.5 pi rho r squared v cubed t. The energy depends cubically on the speed of the air. That is to say, that small increases in air speed can lead to large increases in the electricity obtained. Now we must bear in mind that the transformation of kinetic energy into electrical energy is not perfect. Real systems are never ideal, they have losses and imperfections, and therefore we must consider a performance factor that we will call eta, and that will always be, by definition, less than 1. Typically it is around 0.5, that is to say that yield is usually around 50%. We have in our equation an uncomfortable factor, which is the time t. The energy obtained, obviously, depends on the time that we remain measuring. For this reason, power is a much more suitable magnitude, since it does not depend on time. Power is equal to energy divided by time. taking into account the results obtained. P equals eta 0.5 pi rho r squared v cubed t equals eta 0.5 pi rho r squared v cubed.